Okay, let's dive straight in. We're looking at simulating environments with reasoning models for agent training. This is a really significant paper from folks at the University of Washington, Microsoft, and Carnegie Mellon. And if you just need the quick takeaway, the 1-minute version, here it is. Training capable LLM agents. It's massively bottlenecked. You always need these heavy, custom-built, often quite brittle environments for every single complex task, like, office workflows or navigating specific websites.
Yeah, exactly. And the authors here found a clever way around this. They basically show that LLMs, because they have these powerful internal world models already, can be the environment simulator.
Right.
They can generate realistic feedback, state changes, how tools might react.
Right.
All without actually needing real APIs or real test data during training.
So how do they make that work? They've got these two frameworks, environment-agnostic ones. First is Simia-SFT. That's for cooking up lots of supervised fine-tuning data from just a few examples.
And the second is Simia-RL, which lets you do reinforcement learning, but using the LLM simulator for feedback instead of needing a coded-up environment.
And the results are pretty striking. The models they fine-tuned just on this synthetic data, they call them Simia-Tau, show really consistent gains.
Yeah, their 32 billion parameter model actually beats established closed stuff like GPT-4o on the Tau squared benchmark. It really reframes the whole environment engineering problem. It's less about code, more about designing prompts and schemas.
That reframing feels like the really big shift here. It changes how we might approach agent development. So let's step back for a sec. Help us situate this. You often talk about two main kinds of agent challenges, right?
Precisely. Yeah, think of it like this. On one side, you have tasks where agents are already quite good. We call these complex task simple environment situations.
Okay.
Think about math competitions or coding challenges or even some classic video games. The environment. It's neat, compact, rules are clear. All the difficulty is in the task logic itself.
Right. The agent can just focus on reasoning because the world is predictable.
Exactly. But then you run into the second category, which is frankly much more like the real world, simple task complex environment.
This is where things get messy.
Totally. Like, think about trying to automate booking a multi-leg trip with preferences, or getting an agent to handle a sequence of tasks across Outlook, then Excel, then maybe some internal company software.
The individual steps might be easy click here, type this, but the sheer number of tools, the messy interfaces, all the possible errors and edge cases, it just explodes.
And to handle that, agents need robustness, which means they need training data, lots of it. Diverse examples of what works and what doesn't.
And that's the bottleneck you mentioned. Building the actual environments to generate that data is the nightmare part.
It really is. It's slow, it's expensive to build and maintain, and crucially, it's super tightly coupled to every specific tool API you want the agent to use.
So if an API changes or you want to add a new tool,
your whole training setup breaks. Or needs a massive overhaul. It just doesn't scale to the kind of complexity we need for truly general agents.
Okay, problem established. We need scalable, diverse training data for these complex multi-tool settings, but building the environments is the blocker. So this paper's big idea, the core observation, is that the LLM itself can simulate the environment's response.
That's the leap, yeah. I mean, think about what an LLM already contains from its own training. It's seen countless examples of how the world works, how software behaves, common error messages, plausible sequences of events. It has an implicit world model.
So they're tapping into that latent knowledge.
Exactly. Instead of the agent making a real API call, its intended action goes into this LLM-based simulator.
Can you walk us through a simple example? How does that simulation reasoning actually work? Because that feels like the magic trick here.
Sure. Let's say the agent decides it needs user details. It formulates an action, maybe like get user details with a specific user ID. Now, in a traditional training setup, that would have to hit a real database or a mocked API. Might be slow, might cost money. Maybe the test database isn't even fully populated.
Right.
In the Simia approach, that get user details action goes to the LLM simulator environment.
Yeah.
The simulator looks at the current situation, the conversation history, the formal description of what the get user details tool is supposed to do, its inputs and outputs.
Yeah.
And then, using its world model, it just reasons about what a plausible, realistic response would look like.
So it just makes it up.
Well, makes that up. Sounds a bit random.
Yeah.
It generates it, constrained by the tool's schema and the context. It might produce a full JSON object with a user ID, name, email, maybe even plausible-looking purchase history, all fabricated by the LLM, but looking exactly like what the real tool would return.
Wow, and the agent gets this fake JSON back.
Treats it as real environmental feedback and carries on with its task. It has no idea and doesn't need to know that the environment isn't real in the traditional sense.
Which means you can generate data almost endlessly, right? As long as the simulation quality is good enough.
That's the scalability win. It fakes the tool responses so well that the agent gets the feedback loop it needs to learn, but without the massive engineering overhead of building the actual tools or environment backend.
Okay, let's dig into their first framework, Simia-SFT. This is the one for making supervised fine-tuning data without needing the environment implementation. What's that pipeline look like?
Right. It's a neat four-stage process. It's really designed to make sure that even though the data is synthetic, it's still high quality and usable for training. Stage 1 is LLM-based pre-filtering.
Pre-filtering, why start there? Why not just jump into synthesis?
Good question. You need some starting material, right? A small set of really good example trajectories or seeds. The pre-filter is about quality control on those seeds. It runs 3 checks. First, a completeness check. Did the example actually solve the task successfully? Second, a logic check. Does the reasoning make sense given the actions taken? And third, super important, a format check. Is the structure right? Are the JSON outputs correct? Function calls formatted properly.
And bad seeds get thrown out.
Yep, keeps the quality high from the start.
Okay, clean seeds acquired. Then stage 2 is prompt design. This is that engineering shift you mentioned.
Exactly. This is where the human effort goes now. Instead of writing Python code for an environment, you write really good prompts for the LLM synthesizer.
What goes into that prompt?
It's quite detailed. You need the formal specifications of all the tools the agent could use. You need the rules or policies for the specific task domain. You need the expected formats for inputs and outputs. And crucially, you include one of those clean seed trajectories as a reference.
Like an exemplar to keep the LLM on track.
Precisely. It anchors the generation, making sure the LLM produces interactions that are relevant to the task and use the available tools correctly.
Makes sense. Then stage 3 must be the actual simulation.
Right, LLM trajectory simulation. They used powerful models like GPT-4 and Claude 3 Opus, I think they mentioned. Oh wait, no, GPT-5 and O4 Mini for generation here. Anyway, this model takes the prompt and starts generating new multi-turn interactions.
So it goes back and forth. User query, agent thinks, calls a simulated tool, gets a simulated observation.
Yep, cycles through that until the simulated task is done. And they specifically mention adjusting the temperature parameter here.
To get more variety in the generated trajectory.
Exactly. Avoids just getting minor variations of the seed.
Okay, but LLMs can be, well, messy. Especially with complex formats like JSON or nested calls. How do they ensure the output data is actually usable for training? It needs to be perfect, structurally.
That's the critical fourth stage, rule-based post-processing. You can't just trust the raw LLM output for training data. This stage is like a cleanup crew. It fixes common errors, like malformed JSON, missing commas, wrong brackets, all that stuff, and it does a strict validation. Does every tool call the agent made in the trajectory actually refer to a tool that was listed as available in the initial prompt?
Sanity check. Ensures the agent isn't hallucinating tools that don't exist in its world.
Right. This final step makes the data truly training ready.
That sounds like a pretty robust pipeline for SFT data. But, okay, what about reinforcement learning? Simia-RL. That feels like a bigger jump. Can you really use an LLM simulator effectively within that iterative RL loop?
Yeah, that's often the tougher nut to crack. RL usually demands those custom environments and specific reward functions for every scenario. It's a huge engineering lift.
So how does Simia-RL get around that?
It integrates the LLM simulator directly into the RL training process. They used a method called GRPO for policy optimization, but the key is the simulator replaces the traditional environment.
So the agent proposes an action. It doesn't hit code, it hits the simulator again. What does the simulator do during RL?
It serves 2 main roles. First, just like in SFT, it does the environment feedback simulation, takes the agent's action, generates the plausible tool output or error message.
Okay, same as before. What's the second role?
This is maybe the more audacious part. reward computation.
The simulator calculates the reward.
Yes. The LLM simulator itself is tasked with looking at the agent's trajectory, or its actions so far, comparing that against the task goal, and then assigning a reward signal.
Wow. Okay, hold on. How reliable is that? You're trusting the LLM's judgment not just to simulate the world, but to evaluate the agent's performance within that simulated world. Isn't there a risk the agent just learns to please the simulator, not solve the actual task?
That's the classic sim-to-real question, absolutely. And it's a valid concern. The key, they argue, is how heavily constrained the simulation and reward process is.
By the prompt design again?
Exactly. The tool specs, the explicit success criteria defined in the prompt. The simulator isn't just randomly deciding good job, it's reasoning. Did the sequence of simulated actions, using the allowed tools, lead to the formal goal state defined in the prompt?
So it's a constrained evaluation, not free-form.
Right. And this provides that necessary turn-by-turn feedback loop for policy optimization like GRPO needs, but it does it across potentially thousands of different scenarios, all handled by the same core simulator framework. That's the scalability gain for RL.
It's still kind of mind-bending that it works well enough for optimization. Okay, let's talk payoff, the numbers. How did Simia actually perform against the big names?
The results, especially on the tau squared bench, which includes things like complex airline booking and retail tasks, were genuinely impressive.
Okay, give us the headline numbers.
All right, so their main model, Simia-Tau, built on Qwen 2.5 3D2B and trained heavily with this synthetic data. It scored an average of 58.9 on tau squared.
And how does that stack up?
Well, it beat GPT-4o, which averaged 54.2. And it even surpassed a much larger model, XLAM 270B, which got 56.3.
So better performance than bigger, closed models, achieved through better, more scalable data generation.
That seems to be the story, yeah. Significant leverage.
And this wasn't just for huge models, right? You mentioned smaller ones, too.
Absolutely. They showed impressive results with an 8 billion parameter model, too. Simia-Tau, based on Qwen 3.8b, scored 49.3 average.
And for comparison,
that single 8B model outperformed GPT-4, the standard one, which averaged 45.4 on the same benchmark.
Wow. Okay, that really underscores the efficiency gain from simulation. What about robustness? Raw success rate is one thing, but real-world agents need to handle hiccups.
Good point. They looked at that using the passive trick metric. Basically, does the agent succeed if you give it a few tries, like K1, 2, or 3 attempts?
Right.
And their Simia-Tau 32B model was consistently better than the larger XLAM 270B across all values of K. It had higher pass rates, suggesting it's more reliable and robust, probably because it was trained on such a diverse set of simulated scenarios, including failures.
That makes intuitive sense. If the simulator generates lots of weird edge cases or common errors,
the agent learns to handle them. Did this hold up in other areas, like office tasks?
It seems so. On Office Bench, which is all about cross-application stuff like coordinating calendar, email, presentations, their Simia-OB model, again using the 8B Qwen 3, scored 44.0 average.
And GPT-4?
Way lower, 31.1. So again, a big jump, especially in these complex workflow scenarios where integrating different tool logics is key.
Okay, there's one more result I think we need to touch on: the ablation study. This really gets to the core sim versus real question. What happened when they compared simulated data to real environment data directly, but at the same small scale?
Right, like comparing 5,000 simulated trajectories versus 5,000 collected from a real coded environment.
What they found was interesting. The performance was comparable. Sometimes the simulated data even did slightly better.
Really?
But that wasn't the main point. The real advantage wasn't that simulated data is inherently better per sample. It's that you can generate so much more of it.
Ah, the scalability again.
Exactly. Getting 90,000 high-quality trajectories from a real environment, basically impossible or prohibitively expensive. Simulating 90,000 trajectories. Computationally intensive, sure, but feasible.
So it's not magic data, it's just more data, which leads to better models. The simulation removes the data bottleneck.
Precisely. It shifts the cost from environment coding and maintenance to compute for generation.
Let's talk about that feedback richness again, especially for RL.
Yeah.
You mentioned the simulator gives better error messages. Can you give that example comparing real versus simulated failure?
Yeah, this was a great illustration of the paper, figure 8, I think. Imagine the agent tries to schedule a meeting at a certain time. In a typical coded environment, if that time slot is busy, it might just get back a generic error like, failed to create a new event.
Which tells the agent almost nothing useful for learning, right?
Exactly. It failed, but why? What should it do differently? Who knows?
So what does the Simia simulator do?
Because it's reasoning based on the simulated state, it can provide much more detail. In the same situation, it might return something like, failed to create a new event. The time slot conflicts with an existing event, lunch break from 12.0000000000.
Ah, that's actually useful. The agent now knows why it failed. There's a conflict. It can learn to, say, check the calendar before trying to book next time.
Precisely. That richer reasoned feedback is incredibly valuable for the RL policy optimization. It helps the agent understand the consequences of his actions within the world's dynamics.
Which likely contributes to why the Simia-RL approach worked so well.
I think that's a big part of it, yeah. The agent isn't just learning that it failed, but getting clues about how it failed.
Okay, we've covered a lot of the strengths, but let's be balanced. What limitations did the authors themselves point out?
Well, a couple of key things. First, while they tested across several domains, airline, retail, office, it's still a finite set. Applying this successfully to truly open-ended, constantly changing web environments is still a significant next step.
Makes sense. And the other big one, that sim-to-real gap we mentioned.
Yeah, that's always the potential catch with simulation. Even with all the constraints from tool specs and schemas, the simulated world might still have subtle differences, distributional biases, compared to the real thing.
So an agent trained purely in simulation might hit unexpected issues when deployed against real APIs. Maybe they're slower or buggier or just behave slightly differently than the LLM predicted.
Exactly. It's a risk that needs careful evaluation and probably some fine-tuning on real data eventually for robust deployment.
Okay, so wrapping this all up, what's the big picture takeaway here? What does this paper really establish for how we should think about building agents going forward?
I think the core conclusion is that environment simulation using LLMs isn't just a theoretical nice-to-have anymore. It's a practical, seemingly very effective strategy for training agents. They've shown a path to scale research and deployment on complex, real-world style tasks.
And it marks that fundamental shift, right? The heavy lifting moves away from painstakingly coding environments.
And towards the perhaps more agile process of designing effective prompts and clear schemas for the LLM simulator.
So thinking about this for you, the listener, maybe designing the next generation of agents, does this change the calculus? Instead of pouring endless resources into building hyper-realistic digital twin environments, which are complex and need constant updates.
Should we be asking, if the LLM is already a powerful enough world model to simulate the necessary dynamics for learning, is the future more about perfecting the prompt that guides that simulation rather than perfecting the external environment code itself?
And what does that mean for how we even think about external tools and APIs? If most of the learning can happen internally via simulation, maybe the real-world interface can be simpler, focused just on execution, not complex training feedback.
Definitely some interesting architectural questions to ponder as the lines blur around what an environment even is in this new era.
A lot to think about. Thanks for breaking that down with us.